All right, so we started the topic of ordinary differential equations last time. We're going to be solving them numerically, so you have a class, a separate class from this one, where you learn how to solve equations analytically. If you can solve analytically, that's very powerful. It gives you a formula that you can just plug in a value into and get the value of the function that you're looking for, but that's not always possible. Okay? And sometimes we don't have problems formed in terms of functions. Sometimes we have a data that is acting instead of functions, so we need to be able to work with the most general thing we have. Okay? So we introduced basically so-called initial value problems, okay, in form of dy dx equals to f of xy. And we said the simplest possible method is so-called Euler's method. It's going to start from a value, which is initial value. So I'm typically solving on an interval. Let's say that my interval, what is example here, my interval will be 0 to 4. Okay? So I start with the value at 0, and the next value I get as follows. So this is my, let's say that this is my 0. This is the function or the value of the function at 0, or whatever my initial value is. So I start from here. That's a known value. After that, I just say, okay, I know that the slope, which is dy dx, this is a slope. Okay? The slope at this point is known. It's actually just evaluating this f of xy, which I have. So I know that slope, so I'm just going to take that slope for a step h to my next value of x. So my predicted value will be this one. I literally took that slope for this step h, okay? And this is going to be my f of xi plus 1, which is yi plus 1. So my yi plus 1, okay, is the value at xi plus 1, and I get it by taking the value that I already know, plus my slope, and the simplest way to determine slope, this is sort of a first order estimate, is f of xi yi times this h. And I pick h, so that's my discretization spacing, and the smaller the h, the better, because I'm going to be making smaller mistakes. So you will actually go and program Euler method. You can call that function Euler method. Okay. Or you could so basically call it Euler method.m. And you will be solving the following problem. Now this is a simple problem. You could actually technically just integrate and find what analytical solution is. Analytical solution is actually given here. Right? But we're going to use analytical solution just to see how good are we, how well are we doing. Okay. So this is going to be f of xy. Technically it's really f of x, so that's what makes it simpler to integrate. Right? So you'll just work with it as is, okay, and just do this iteration. And the key thing is that you have to ask user, what will be the interval start? For us it's going to be 0, okay, and the value at 0 is 1. So your first two values that you're starting from are 0 and 1. And every further y you will get by applying this formula. It's actually a very simple for loop. And of course you need to know when to stop. Okay. So your end of the interval, let's call that xn, okay, is 4. Alright, open up MATLAB and type away. And I want as an output vector values x and y. Okay. And I also want you to compare. So once you have the function, you can execute it for different h, different spacing. So I want you to go down in spacing and see how the method improves. Okay. So this is what you're shooting for. Okay. Large spacing, larger error. The smaller I get, the closer I am to the analytical solution is actually plotted in black here. Alright? Get at it. And we'll be walking around helping as necessary. So most of the formulas and everything is given here. There's a PDF of these slides if you want it on your own computer.
We're going to make a function.
Yeah, and call it Euler method. And there's what should be input, what should be output. And needless to say, I want you to upload this tonight. It should motivate you. Nothing happens without a little push, right? Gentle. Yes, so the function on the right is your f of xy. It's really f of x, but in this particular case. Yeah, it's minus 2x cubed plus 12x squared.
So do we have, okay. So x1, y1 would be your starting point.
Yes.
Oh, 0, 1.
Or you can call it x0, y0, however you want. But it's your value, the starting value is 0 for x, and the corresponding value of y is 1. And that's that point you're starting from. And after that, you're kind of building the solution further. So you will find your values of y only at these specific points that are h apart. That's how you're numerically solving things, right? And that's what I call by discretizing. So I discretize my interval in spacing h, and I'm finding the solution at every h apart. You never find the whole thing. You cannot find the whole thing. Not numerically, anyway. Why? So that's my. Okay, so this point, I gotta start from a point. This point, right? So I'm starting from a point, I'm saying it's 0 in this case, that's your x1. And the value at x1 is 1. Okay? So in order to get y2, you're gonna put y1 plus f of x1, y1, which is 0 and 1, times h. And h is something that is input to the function. Then you're gonna go to y3, right? And y3 will be y2 plus f of x2 y2 times h. And then you're going to keep going until you get to the end of the interval. Okay? And your x's are all h apart, so that's how you get your next x, right? So they start at 0 and they're all h apart. So you're building your solution 1 point by 1 point. If you need to, always take a piece of paper and write down for something simple, for h is 0.5 or even 1. So for large spacing, you can do this by hand. Okay? Find what your values should be by hand. And see that, understand, and then write that for loop that will actually just do it all for however many components.
So you want this to
I want output vectors x and y values should be output, and then you can just say plot xy.
This is
Lecture 8.
Yes. Do you want the analytic too?
Yeah, it's easy to plug in.
That's gonna be a different output. No,
Yeah, so it's going to be slightly different. Yeah. We know how to plot a function by now. Right?
Yeah.
So that you can do at the end. But this is how it's supposed to look like, approximately.
Can we go back? Oh, sorry. No, you're fine. I meant, you already went back when I said
What age
Oh,
are you using?
so back.
What age should you use?
The smallest one, or anything, really. You just want the smooth plot. And smooth plot, you get the small spaces. So x are the x values that you're looking for a solution at. You're looking for y evaluated at x values, and those x values are between 0 and 4, h apart.
And what is the capital H?
Oh, I'm sorry, that's a typo. That's PowerPoint doing capitalization for me. And it's doing it again. There we go. It's PowerPoint being smart. Overly smart.
Unless it changes as you there's no why it's actually I didn't see that. Then it's more Yeah. You may have to report, I didn't see that in the top. So you use the.
Shouldn't it be x1 to xn?
As well as actually, I don't know the book. Reset that. I was gonna get up and I said I'll start.
Because you have to.
Did
you put either the y of x under?
Well, so it's looping it, but it's like looping all the each loop as opposed to the first one.
But why were you the y of x? Y of x and f of x.
The f right there, the b by the so through 10 times, you're getting the 10th and it's the first
How are we doing?
We're doing. We're doing. Okay,
Doing really well. Or maybe mine, I don't know, this looks good and your approach is maybe mine is, I remember now, I remember. Let's go over.
This is your really nice stuff. Like that's what it's supposed to be. Because you need to have one set. Like that and everyone else. That's what I was thinking. I'm trying to be set if I can get to
So this is a slight variation of this problem. So I just said this is, I was comparing them all because we will do more methods than just one. So I call this actually function Euler stepping. So I have x, y as an outputs, and I just called it Euler stepping. x1, y1, and some maximum x and 0.5. Okay? And here's my Euler stepping. I create myself my x vector. These are x's from my interval start to interval end h apart. Okay? I can initialize my y values by zeros, and I just set the first one to be y1, which is my input. Okay? And this you can do in various ways. You can start from 1 to length of x minus 1, okay? And then you would do here I plus 1, so it would look precisely like that formula I put on the slides. And I actually had separately programmed what is this f function. So this is a matter of design. You can just write it in directly. Or you can have a function that basically computes f. In this case, it's really just f of x. So I had a separate function. That's up to you. But this is it.
But could you do for I equals 2 to
Yeah.
and
I did that initially and I changed it as y. But then you would have y of I is y of I minus 1, f of x 1. So I changed it to be a little more similar to the formula. Does this make sense?
Does not be that language. I don't understand why there's so many functions inside that.
Oh, I was actually doing for, we're going to come up with more methods than this one. Okay, so I have one code that does comparison of all. Now, in order to put that plot up, we're going to go to Hoynes method, Runge-Kutta, and so forth. So there will be more methods. So I just have a one master. And then outside of the loop, I first evaluated for h is 0.5. Okay? And I set these values 0, 1, and 4. Then I evaluated for 0.1 and 0.05. And then I plotted. So these are all of these, and I also can plot my analytical solution very fine, so I have it looking really smooth. And then I'm plotting all of them. Okay, so let me evaluate this to see what I'm getting. I wrote the function, I called it slightly differently, Euler stepping.
Yeah, like you run the math f of x, I, y. Can I see that function?
F of, evaluating f? Sure. Here it is. It really doesn't depend on y, but I just wrote it to have more general code so I can easily replace. More questions?
Did you do a script with all the plotting? Did you run a script?
So this is actually this at the very beginning. So these were actually all sub functions in my. This is really a script. I don't have inputs or outputs. Okay. So I set what this in, and then I just evaluate like this. So that would be that script that you're talking about. So sort of a master script that is executing everything. Right? More questions?
So your y is so your for loop for the y is 1 to the number of the x minus 1. Right?
Yes. Yes.
So means the y have like
Well, first one I already have. So the first one is my initial condition, y of 1, right? So I could run this as this. So for I is starting from 1, but I'm really evaluating y2 first, right? Or I could start 2 to length, so I'll rewrite this. This is how it was actually. I could do this. And then my y of I would be here minus 1, minus 1, minus 1. Yeah? Same thing. Clear? More questions? So this is the main function, okay? Or up to here. This?
This is not enough for.
What's your question? Oh, so this is just evaluating my f.
And then what do you plot?
So what I plot is, so I call this function 3 times. This is why I wanted you to do a function. I asked you to name it Euler method. So I call it Euler stepping here, and I call it for different h. 3 times. And in all 3 times, I remember what the output is. So xy, x2y2, and x3y3. I also separately plot my analytical solution also at whatever x's you please. And then on the figure, I plot my analytical solution, xy, x2y2, and then I also add x3y3. So they're all plotted at the same time. You could also do with hold on. You plot one by one and you say hold on. And I also give it a legend. So when I execute, this is what I get when I execute. So again, I'm getting closer. Yes? So derivative dy dx, that's your element. Okay? So it's minus 12 something. Okay. So everything we now do from now, again, finish this up by tonight. So everything we do from now, it's really just changing this slope here, or what the estimate for the slope is. So I want it to get better and better. So this initial one, it's not the ideal solution, okay? I would like to get something better or more accurate. And I will mention now 2 different methods that are actually much better, okay? So first one is so-called Hoynes method, or modified Euler. All it does, it's going to adjust the slope a little. So in Euler, I said, let that slope be f of x I, y, I. Okay? Well, Hoynes said, okay, how about you take the average of the slope at this point and slope at this point. That's it. Okay? So basically, my adaptation of this, okay, will be that my slope will not just be f of x I, y, I. It's going to be average of the 2 neighboring slopes. Okay? And I'm hoping that that's going to be more accurate. Okay? And you could actually iterate this multiple times. You can do this a number of times. So again, your prediction based on the tangent would just follow the slope at this point. The slope at this point is slightly different. It's actually this one. Okay? So the average of these slopes in this particular case works a little better because this yellow line gets you closer to the actual solution. Okay? That's the idea of it. It doesn't always have to work, but this is somebody said, okay, maybe this is how we can improve. So basically, instead of having f of x I, y, I here, I'm going to have f of x I, y, I plus f of x I plus 1. I'm going to estimate this y I plus 1, 0 or prime here. Okay? So this is what my y I plus 1 from Euler's method would have been. Okay? So at that point, like, I estimate what my f would be, and I just average the 2 slopes, and that is my Hoynes method. So it's really just trying to improve on this initial slope that we're using to solve the problem. And you can actually do this multiple times. You can actually try to keep looping, and here do the estimate, improve the slope, do the estimate again, improve the slope, and do that a couple of times before you actually move on to the next step and accept the solution. So in that case, you can iterate on this so-called, this is called corrector equation. Okay? So you can do another loop within here 6 times or so to improve on it, and then move on.
So,
Okay.
mine is
So Horn is going to be a little more accurate. So here's an example. If you had an Euler method, that this is one example that I showed before, you would get this much closer. So maybe you basically somehow executed Horn's method in your instead of your Euler. Okay. Super accurate one is called so-called Runge-Kutta fourth order, and this is to date one of the most used ones. Now, what it generally does, it takes a bit of a complex average of 4 slopes before it actually accepts a finite slope and moves on with it. And before I actually show you, do I have this example? No, I don't have. I'm going to actually show you how accurate it gets before I explain how it works. So this would be actually on that same problem that we were solving now. If you did Horn's method, it would actually get pretty close. Okay? So this would be Euler for point 1. The solution, analytical solution, is still in black, and the red one is Horn's. So it's a definite improvement over Euler for the same H. Okay, I get much better for the same H. Now look at Runge-Kutta. Even for a very large H, large spacing, 0.5, okay, I'm going to get on the money. Okay? Here in between it's linear, that's because of my spacing. Okay? But all of the points are basically on the analytical solution. Okay? So this is very accurate. It's a little more expensive. Okay? But you can, if you can afford this Runge-Kutta, then you should do it. Okay? So let me now explain how does it get so accurate. It's kind of feeling out all of the slopes until it really gets it correctly. So basically what it does, I have my solution xi and I have yi. So this is the starting point. Okay? Then I say, okay, instead of just going with one slope, I'm going to work with the slope a little. First, go halfway. Okay? For halfway, estimate with Euler what the solution would be. Here. And then this is my slope number 1. Okay? Then from halfway, okay, at halfway I know what my slope is. Take that slope, okay, and I'm going to call it K2. At the K2, go again from this point with that slope K2 and get over here. So I have slope 1. That's just my regular Euler slope right here. Okay? And I get to this point. So for this point, I know I can find the slope at this point because I have both x and y at this point. So I take that slope as slope K2. Okay? And I'm going to go back and start from the initial point with slope K2.
oh,
And I'm reaching this point now.
okay.
Alright? Then at that point, okay, I start from the initial point, and I just go with this slope K3 at this point. I go all the way entire H. So this is my third slope. And then finally, what I'm going to take as my final, so at this point I also have a fourth slope, okay? And I'm going to take a weighted average of these 4 slopes. Okay? And this weighted average, my final slope would be 1/6 over first slope plus 2 times second slope plus 2 times third slope plus.
Oh, I get it.
Okay.
Fourth order now.
So now why does it work? We don't have enough knowledge here to analyze this and why does it get you so accurate, but it does. Okay, that's something that is not for introductory course numerical methods. Okay, but you do the analysis and really it gets you closer. Somebody didn't just come out of this. There's calculus behind this that allows you to get to this. Okay, so it's not that somebody just thought of it. Oh, let's take these 4 slopes because they look cool. Okay? There's a reason why they're taken that way. But ultimately, what you get is just formulas. So you get formulas essentially. Your K1, your slope K1 is this first Euler slope. K2 is evaluate f at this halfway point. And this is what your first halfway estimate with K1 was. Evaluate K3, evaluate K4. You ultimately have formulas and you write a formula. Okay. All right. See you Friday. I can have questions.